All right, I think we can start. Yeah. Just 1 second. Okay. Hello, everyone. Welcome to this new edition of Spinal Cord Toolbox course, which is going to be compatible with the version 4.2.1, which was released about a week ago or 2 weeks ago. Some changes compared to the previous courses. Maybe before I start, I'm Julien Cohen-Haddad, and we also have Olivier Vincent, who is right here, and is going to basically help you all getting the bug fixed. And so the one aspect of this year's course is that the course material is now hosted on Apple iCloud, which makes it easier for updating versions and sharing and so on. So if you want to see the presenter notes, which is basically the what I'm going to say, you can click on the show presenter note here. So the outline of the course is the following. Quantitative MRI of the spinal cord. I don't need to say much about this. You already know the rationale for running all those different MRI metrics in the spinal cord. The rationale for developing spinal cord toolbox is that that there was a gap in terms of image processing software for that are specific to the spinal cord. So we didn't want to reinvent the wheel and replace FSL or SPM, but really to create a comprehensive toolbox that would fill the gap of the specific missing functions from the already existing software. So you could see SCT as more of a pre-processing, and if you're doing fMRI analysis, for example, SCT does not do any GLM, right? So the idea is that you would pre-process your spinal cord data with SCT, and then you can run traditional tools and GLM and first and second level analysis with your favorite package. So it's an open source library. It's licensed under the MIT license. It includes segmentation tools, template and atlas, registration framework, atlas-based analysis framework, as well as other tools, including motion correction. By the way, if you have any question, just feel free to ask, to interrupt me at any time. I really want this course to be interactive. That's really the best way for you to learn. And some of the methods that are implemented in SCT have been published in various papers, and they're listed here, and as well as on this GitHub website. There are various applications of SCT so far. On quantitative structural MRI, including diffusion or magnetization transfer from the group of UCL, Marseille, Montreal, UBC, Sweden, UCL. Applications with functional MRI. Joe published a study where SCT was cited and partly used. Also a group of Julien Doyon in Montreal, Falk, and other applications with functional MRI, applications in patient population as well, in MS, different myelopathy, as well as infection, ischemia, And just going to show you like some examples of studies that have been done. So, for example, the UCL group, Marius Yanakas led a study where the idea was to compare different registration, like different segmentation methods. So it's we've seen the tool of Mark Rosfield during the workshop, and even though there is a bias in terms of the definition of the boundary around the spinal cord, the precision, the reproducibility is still comparable with the semi-automatic or manual methods with SCT. So that was the conclusion of that study, one of the conclusions. SCT also enabled to start doing multi-center studies without any user bias. So basically, all the studies, all the subjects from different centers, London, Vanderbilt, Montreal, were registered to a single template. Similarly to when we do brain images and we register brain data to the MNI template, for example, it is now possible to do that also in the spinal cord. Another more recent study where this multi-center approach was extended to a larger population of 642 MS patients across 13 different sites, and the idea here was to derive a probabilistic atlas of or probabilistic mapping of MS lesion appearance. In addition to MS lesion segmentation or cord segmentation, we can also do gray matter segmentation, and that has some obvious application in ALS, amyotrophic lateral sclerosis. Another recent study was done by the group of Chulus Dewal in Chicago at Northwestern University, and they applied SCT to look at tract specific analysis in stroke patients. They notably showed some abnormal FA ipsilateral to the location of the stroke. Also, a fairly recent study was done in collaboration with MGH in Boston, was to basically use SCT to analyze PET data. So this data were acquired in patients suffering from a chronic pain disorder, and they were submitted to a PET MR scanner, and SCT was used to quantify the agent, the radio tracer at specific location in the spinal cord in those pain participants. So that was a quick overview of like an example of the kind of application that SCT supports. So in terms of technical details, we support directly OS X as of 10.12, as well as all the non-Linux distributions that we've tried so far. If you have like an uncommon Linux distribution where SCT does not work, please let us know. And Windows is supported via Docker or virtual machine as well. So that those two options. Interface is it's a command line interface, although we are working towards integration with FSLIs. There is no other dependent software. It's based on Python 3, some of the C++ compiled code as well. And we do extensive testing using the Travis platform. And what is packaged is basically some binaries that are OS specific and the source code. So installation, I guess we can go quickly through that since almost everyone here has SCT installed. First of all, I recommend you to open the terminal. So we're going to do that here. It's useful to have a terminal with 100 columns. It's a detail, but makes things more easy to view. It would be nice if you could get acquainted with some of the basics Unix commands, where basically the terminal seems a bit scary at first, but it's really a way to communicate with your hard drive and the files that are installed. And if I open a Finder, for example, here, I go to my home directory or to my desktop. You see that I'm a fan of Anthony Bourdain, for example. You can basically see the same thing from your terminal, right? So basically, the terminal allows you to look at the files, to do to navigate across the different directories and so on. So I encourage you to learn the basics of Unix, because this will be useful in the long term. And that's also the same type of commands or the same type of interface that is used with FSL or FreeSurfer or other software. In terms of image viewer, you can pick your favorite ones if you're already familiar with your nifty viewers. We like to use FSLIs. We are just used to it. MITK Workbench is also a very nice viewer. In terms of DICOM viewer, if you have an OS X platform, you can use Osirix or Horus. Okay, so let's get going. So in terms of installation, I guess you've already went through that, but the idea is that you would go to the main repository of SCT, and then you go to installation, and then you can decide to install the package, like a stable release, or the latest GitHub version. So depending on if you want to, if you're brave and adventurous, you can just go with the latest GitHub development, knowing that there might be some bugs or things to fix before releasing a stable release. But be also aware that even with stable release, there are also things to fix. A software is an organic object that always evolves in time. The nice thing with release is that if you're planning to publish a study, it's always good to stick to a particular release and do your entire study with a Git release, and mention also the release that you've used in your paper, so that it enables other people to reproduce your analysis in 20 years from now. So once SCT is installed, you can just make sure that it is up and running. Just going to make it bigger. Can everybody see here in the back? Okay, I'll make it a little bit bigger. So I'm going to type SCT check dependencies. It shows a bunch of information from your OS, RAM available, and it just checks the basic dependencies that should be installed and working. If you're connecting via SSH to a cluster, for example, if you want to run SCT in computer clusters that you have at your institution, the last one will show a fail, and that's because you won't have the interface available unless you do like an X tunneling, for example. But that's a detail that we don't need to talk about today. If you want to run a more exhaustive testing, you can run SCT_testing. It uses parallel computing. So basically, if you have like multiple cores, it will run one function per core. And that really tests all the functions of SCT to make sure that your installation is correct. So if everything is green and okay, then you're good to go. If not, raise your hands, and Olivier will come to your rescue. Okay, we have two of them. It's okay. So yeah, you have, yeah. So any questions so far? Is it fixed on your end? Yeah, cool. Okay, I guess we can get going. So first thing to do is to download the course material. So you see that SCT testing finished to run and everything is okay. So we're good to go. So we're gonna go to our home directory, or you can go to whatever directory you wanna go to, and then I'm going to download to run this command to download the course material locally. So I just did like copy paste from this course material to my terminal window, right? So in my case, I have curl. Curl is a Unix command to download data from the internet. If you don't have curl, you might have wget. If you don't have wget, then you can also go directly to the OSF website. So I'm going to show you here. I'm doing a copy, paste. That's the OSF website where the course material is hosted. So you can also just do a download and it will download the course material in your station, right? So still downloading. Of course, like sorry, can you repeat your question?
So it's still running for the app testing.
It's running the SCT testing, right?
Yeah.
Okay.
It takes longer.
Okay, yeah. You can also interrupt it if you want. If everything is green so far.
Yeah.
Yeah, the speed depends on the number of cores. But if everything is green so far, if you want to move on with the course, you can also interrupt it by typing Control-C, for example. It's taking a bit of time. Fortunately, we won't have to rely on the internet after this step. So. Okay, good. Once this is, so we can verify that the file has been downloaded. It is here. So now I'm going to unzip it. It's a zip package, so you can just copy and paste here. And then you can go inside the folder by typing this. So CD, SCT course, London 20, single subject. Okay. So we can move to the next slide. What's inside the single subject? There is a batch file called batch single subject.sh. You can also look at it from your OS GUI. So this is going to be this one, single subject, bash, single subject. So you see it's a batch file that has a lot of commands, right? Basically, it has all the different commands that we are going to run during this course, right? So it goes to a particular folder, which is what cd command is, come to directory data t2. Then it runs propseg. Then it goes to another directory, runs propseg, then runs dipseg, and so on, right? So today we're going to follow all those different commands. The philosophy of a batch script is that you can also run it entirely automatically. If you want to do that, you can just run this chmod 775 to give executable rights. And then you just type batch single subject, enter, and that's it. It will run all the commands automatically. I'm going to stop it now because we want to do it step by step. The purpose of the course is to understand what's behind each command, right? Okay, so that was it for the installation. Now we're moving to the segmentation part. A little bit of theory. So originally, SCT featured propseg, which is a 3D mesh that evolves based on the contour, based on the gradient of the chords and CSF contrast. That's why it's called propseg. Propseg needs an initialization, which is basically finding the center of the approximate center of the spinal cord. And in order to automatize this step, we've also developed Optic, which is a machine learning based approach for finding the spinal cord center line, and that works across different contrasts, T1, T2, diffusion weighted, MT, and so on. If you want more information, the links to articles are also listed at the bottom of the page. And once the chord is identified, there is then an algorithm where this 3D mesh is propagated along the spinal cord. So let's do a bit of hands-on. First is that propseg works across different contrasts, T1-like, T2-like, DWI-like, or T2 star-like. Those contrasts are basically defined on the appearance of the image. You know, if you have a dark CSF and a bright chord, that would be a T1-like. Okay. Otherwise, it would be a T2-like. So we are going to go to this folder, data T2. Okay. If I do an ls, I see that I have a T2 weighted image. Okay. So now we are going to run this command, SCT propseg. -i will be my input image. So in that case, it's t2.ni.gz. By the way, if you're not so familiar with the terminal, a very useful tip when you write command. The reason I'm writing fast is not because I have magic fingers. It's just because I'm using the tab key, which is very convenient. You start writing some names, commands, and if there is only one, so like one existing function that starts with SCT_PRO, by pressing tab. Actually, in that case, there are two. By pressing tab, it just finishes the word, and it's the same for the files that are present, right? So it's very useful to gain time. I will also output the QC, the quality control of the results in a specific folder that I'm going to call QC_single sub. Okay, now I press enter, and it's actually a good example of a problem. What's the problem here is that there is a command line error. Option C needs an argument. Indeed, I forgot to add -c. So if you see this kind of message, this is a easy message to answer. You just add the contrast. Sorry, so T2 here, which I forgot to put. Enter. Then it runs. That's it. So it takes about 20 seconds to do the spinal cord segmentation. And you can look at the results. So let's look at FSLIs. So if you have FSLIs installed, it will output this message. If you have FSL view installed, like the older version, it will output the syntax for FSL view. So I'm just copy pasting these commands, and it will open FSLI's software. And so what we see here is the overlay of the spinal cord in red on top of the anatomical image, right? So you can also zoom in and inspect all your different slices. And you can use Command F if you're on OS X or Control F if you're on Linux to toggle on off your segmentation. Another output is also this QC report that was generated by the flag QC that we wrote here. And similarly, I'm going to copy paste this, and it opens web browser. Okay, in my case, I have other. So what I'm going to do, because I have like old QC, so I'm just going to refresh my QC by deleting everything here. So I'm going to my home directory, where I have the QC single subject is here. So as you saw, I was already playing with SCT for the past couple of weeks, and I've generating a lot of QC reports. I'm just going to delete that folder. And now I'm going to rerun that again, so that I start fresh with only a single image in my QC reports. And then it will append all the different processes that we will see during this course. The nice thing of this segmentation method is that it's fully automatic. So if you run it again, you'll get the exact same results. So the inter process reproducibility is basically a coefficient of variation of 0. Now we can open the QC report. So we can run that command, or you can also go to your home directory and simply double click on the HTML index file. Right. So if I do that, it opens a page on my web browser. And if I click on it, then I see my segmentation result, and I can toggle on off using the right short key on my keyboard. So sorry, yeah.
What do you use? What key? Toggle?
It's the right arrow. Does it work in your case?
Right, yeah.
And so the QC has been done so that it basically finds the cord center, the center of mass of the segmentation, and then it crops around it so that it does enables like a very quick overview of the segmentation results. And by the way, so I can also show you a little bit of this QC report. It shows at the bottom of the page the command that was run, as well as the SCT version. Okay. In your case, it should show something like git like release 4.2.1 or something. depending on what version you've installed. You can also display more or less columns if you want. You can display the path to the file, the type of contrast, for example. So these are all the different informations that you can choose to display or not. Later, I'll show you the search function, which doesn't make sense here because we only have one entry. If you have 2,000 entries, it could be useful to use that. Okay, any questions so far? All right, so let's move on. We'll do the same now for the T1 contrast. So we go back to the T1, to the previous, to the parent directory, and then we go to the T1 folder. If I do an ls, I see that now there is a T1 t1.ni.gz file. And I'm going to run also propseg command. So to be quick, I'm just going to copy and paste this here. Now it will take a little bit longer because the image is also larger. So first, it finds the spinal cord center line, then it does the segmentation, and at the end, it will copy the Q form from the input to the output data, just to make sure that the Q form and S form are the same, because some software deals more with the S form or the Q form nifty parameters. Okay, it's done. So it still takes less than a minute. We can use FSLIs, or we can also look at our QC reports. So if I go back to my browser, I can do a refresh using the command R short key, or in Linux, it would be Control R. And now I can move back and forth between the two processes with the top and bottom arrows. And I can also toggle on and off my my segmentation. So you will notice here that there is some leakage, right? So the segmentation did not work properly on all the slices because of the strong gradient attraction due to this structure here. The spinal cord segmentation leaked. That gave wrong segmentation. So one option is to manually correct those slices. Another option is to try another algorithm, or to tweak the parameters. So speaking of tweaking the parameters, there are different options in propseg that we will not review today, but just to be aware that you can change the initial radius, for example. If you are dealing with pediatric spinal cords, for example, or if you're dealing with animals like mice, the initialization should change, right? And these are some of the parameters that that you can play with. You can also play with the different constraints of the deformation model, the max deformation, max area, the minimum contrast before the algorithm will stop, because it's an iterative algorithm. There is more information on this web page. And as I said, you can also manually correct the segmentation, really if you're desperate. And it's common to do that, right? And lastly, we can look at another algorithm that was developed about 2 years ago, which is called DeepSeg SC.
Could you explain more in detail the options like max deformation?
Absolutely. So max deformation is so the way this propseg algorithm works is that there is a mesh that will be deformed across each iteration, and the amplitude of deformation is driven by this parameter, this max deformation. max area is that for each slice, it computes the area, and it knows that if there is an area of like 200 millimeters square, it's not plausible. So it will basically stop the iteration there. And that's also the reason why the algorithm stops automatically there. You notice that, right? It doesn't go above the brainstem. So it stops, and the reason it stops is because of this max area factor. So if you want to go more up, you can also play with this parameter, right? Mean contrast is related to the contrast of the image. So PropSeg works using a contrast adaptative method in order to accommodate different types of contrast, image quality, coil, like B1 plus profile, and so on. So in order to keep a consistent gradient threshold, it adapts the contrast throughout the slices, right? And if the contrast is too low, it will stop the segmentation. It will not segment the corner. But if you still want to try, then you can change this mean contrast. Right? So let's move on to the next, to the other algorithm, which is called DeepSeg SC. As the name suggests, it's based on deep learning, and as was mentioned this morning by Olivier, one challenge with deep learning with segmentations of very small objects, like objects that takes a very, very small portion of the entire volume, is that there is a large class imbalance. In order to tackle this class imbalance, we first run a convolutional neural network that will find the spinal cord center line, that is used in order to extract a patch around this center line. And then from this patch, another convolutional neural network was trained to identify the spinal cord. So the command now is called SCT DeepSeg SC. And I'm going to copy paste this here. And as you notice, we will output the segmentation in another folder so that it will not overwrite the segmentation that was done with PropSeg. So we will be able to compare the two different algorithms. So DeepSeg is a bit slower than PropSeg.
You mentioned that in the training data there was pathology was included. Is it also applicable across different age ranges?
So people between, let's say 18 and more, the structure, the anatomy doesn't change much in terms of the spinal cord appearance. However, if you want to segment like a 3-year-old, spinal cord, that will have an impact. In order to accommodate, the impact is a size impact. In order to accommodate that, can show you in another terminal window while this is running. If you go to SCT PropSeg, for example, there is an option which is called rescale. And so there's an explanation here. It rescales the image, only the header, not the image, in order to enable segmentation of spinal cords with dimensions that differ from that of humans, or adult humans, should I say. Right? For example, if you want to segment mice, rats, or if you're scanning like a celery in the scanner, you can basically segment any tube of any size if you rescale it properly. Okay, so the process is done. So now we can look at our QC. So I'm doing a refresh, and now you see that you have another entry. Let me call, yeah, I'll just point with my cursor. You have another entry here. So this one is for DeepSeg, this one is for PropSeg, right? So if I toggle between the two, you see that there is a bit of a difference, and especially there is no more there is no more leakage with deep seg algorithm. Okay. I will not go too much in details, but if you are still seeing some leakage, there are other tricks that you can do. For example, data are interestingly noisy. There is a way to reduce the noise level. For example, if you assume that you want a smooth cross-section, that you have a smooth cross-sectional area along the superior and inferior direction, which is not what we assumed at first with PropSeg or DeepSeg, you can still detect the center line and then smooth along the center line in order to have a very well-defined border, and then run PropSeg or DeepSeg. And that will improve a lot cases where there is some leakage. Right? That's a way of regularization, basically, increasing the robustness a lot.
In this case, so how well does this image match the training data that was used for DeepSeg?
Right, so it does match. So the training data was basically heterogeneous, like as heterogeneous as possible to generalize as much as possible.
But if, for instance, we know that a certain case is a little bit different from the database, then you would recommend maybe PropSeg.
Yeah, it's impossible to tell on the right, because there is like more than 2,000 subjects with different parameters, different centers, different morphologies, ethnicities, and so on, sizes, ages, positioning the scanner, coil, scanner, vendors. So, and we really tried to push this heterogeneity. So we could have put more data, but we decided to put less data of a particular center so that it would the model would be representative of the entirety of what's existing. But obviously we don't know what's existing in the entire planet. So it's you know, it's an iterative process. We are adding more and more data into models, which is why it's also important to report the version of SCT that you're using, because you know, for a release in 2 years, maybe the model will change, right? Yeah. Any question so far? So maybe we can move to the registration to template part. So a bit of theory. A template is is like a jargon in our field, in our neuroimaging field, for a common, a standardized structure. There is the very famous Montreal Neurological Institute ICBM 152 brain template that is used for doing group studies to basically have some sort of reference space to realign all the subjects into this reference space. So that was missing for the spinal cord. So in collaboration with the with Aix-Marseille University and the MNI, we created the PAM50 template. 50 stands for the number of subjects that were that are represented in this template. It's 50 adult subjects, and a couple of features. So this template is detailed more throughout all the different publications. There is, first of all, the fact that the template features a T1, T2, and T2 star weighted images. So there are different contrasts depending on the image that you're dealing with. Another recent feature is that this template is fused with the MNI coordinate system. And that is becoming more and more interesting as we talked during this 2 days workshop about the need to unify spine and brain axis into a single studies. And it is now possible to register the subject into a single coordinate space that includes the entire brain, brainstem, and spinal cord. Spinal cord template is straightened, as you see. It was a decision after a long debate, but you know, having a curved versus straight spinal cord. I'm not going to lay down all the arguments, but we decided for a straight spinal cord at the end. There is also vertebral labeling, a spine. It is not shown here, but there is also a spine segmentation that comes with the PAM50. And also probabilistic atlas of the white matter, gray matter, and cerebrospinal fluid. And a white matter atlas, that was the work of Simon Levy, where he digitalized the Gray's anatomy atlas for different levels of the spinal cord, and that was then merged into the PAM50 template. And importantly, this atlas, so if you interrogate, for example, in green, the left corticospinal tract, this is not a binary mask. It's a mask that is, it's what we call the soft mask. It's scaled between 0 and 1, according to, and it encodes the partial volume effect. So if you're in the middle of the corticospinal tract, the value will be 1 because you're completely certain of being in the CST. But if you're at the edge of the CST, you have maybe 0.5 or 0.2 because of the partial volume effect. And we then use, you will see later in the course that we will use that information in order to quantify the metrics, accounting for the partial volume effect. Okay. So how do we register data to the PAM50 template? So we have, you have an anatomical data, which could be a T2 weighted, a T1 weighted, or others. You do the segmentation, then you label vertebrae. And the convention in SCT for labeling the vertebrae is the following. We have either labeling for the vertebrae per se, which would start at 1 for C1 level, 2 for C2 level, 3 for C3, and so on. And those labels, as you can see, are centered at the mid-vertebral body, and it's like a projection onto the spinal cord. Okay. So if you are to produce those labels manually, for example, then that's how you would represent them. Alternatively, that's another feature that came, I think, after an email that Folk sent me, I think 2 or 3 years ago, telling me that he does not have any vertebral body in his like fMRI scans, and he only sees the disc. So Julien, can you please make a picture so that we can label the discs? Now it's possible to label the discs, and that's another convention that includes basically the posterior tip of the spine. It also includes other labels, the pontomedullary junction and pontomedullary groove with values 50 and 49. They are not really used yet, but we have some ideas of how we can use those labels, which is why they exist. Okay. So in order to label those levels automatically, there is an algorithm that is fairly old now. It's based on basically a moving window that is using several priors from the template, the probabilistic distance between adjacent discs, the size of the vertebral bodies, and so on and so forth. And it's robust enough so that even in cases where there is, for example, here instrumentation, and there are some discs that are missing, the algorithm ideally would still be able to label those missing labels. So the algorithm was really designed to be as robust as possible. Of course, it can fail. If it does fail, there is the possibility to do some of the labels manually. So once the levels are labeled, there is a straightening process of the spinal cord. The way that the straightening works is through a thin plate interpolation in order to preserve the internal information of the spinal cord. So it's not it's not a translation. It's like a slice-by-slice translation. It's really trying to compute the orthogonal plane along the center line that is pre-regularized, and then construct a straight space in the output. There is a sexy animation that I can show you here between a curved space going to a straight space. So you see that it's really like a debending of the spinal cord.
Is this affected by the thickness of your slices?
Excellent point. So the straightening, I'm sorry?
What was the question?
So so the question is the straightening affected by the thickness of the slices? So let's say if we talk about axial acquisition with very thick axial slices, the straightening algorithm will not be affected by that. But what will affect the result is the interpolation that is part of the straightening process. And it's very important to keep that in mind, that if you have extremely thick slices, and even worse if there is a gap between your slices, by doing this interpolation to a straight space, you might introduce a lot of interpolation errors. So we'll talk about that further in terms of what's the best strategy then if that's your case. But you might want to avoid doing a straightening if that's your situation. And I'll show you what would be the alternative to that. So there's a straightening process, and once the straightening has been done, there is an affine alignment to the template, which is based on the levels of the levels that you've previously obtained, and then a non-rigid deformation that is constrained in the axial plane. And that is powered by ANTS notably. So speaking of that, this last step, that is basically a slice-wise nonlinear deformation. There is a lot of algorithms that are available in SCT. Those algorithms can be run either on the image, which would be your anatomical image, for example, but it could also be run on the segmentation. Let's say you're dealing with highly artifacted EPI, gradient echo EPI data with a lot of artifacts. The CSF is missing on one slice, it's appearing on the other slice. You have some distortions, there is some Gibbs artifacts, and so on. You know that your segmentation is correct because maybe you manually corrected it. So you might want to rely on the segmentation more than the image in order to register your spinal cord to the template, right? So there is a possibility to do that. There's also a parameter called slice-wise that will ask whether you want to apply those deformations independently on a slice-by-slice basis or regularized across the superior-inferior axis. This parameter only has an impact in some of the algorithms that are listed below. I won't go too much into details, but there is an axial translation, like basically XY translation. There is translation plus the rotation about the Z axis. Affine transformation, a B-spline scene, which is based on ANTS algorithm. So ANTS binaries are packaged inside SCT, and there is the possibility to use either the B-spline regularized form of scene or the scene algorithm, which are very powerful registration methods developed by the ANTS team. SliceReg, which is developed by the ANTS team in collaboration with us. It's a regularized translation across slices that is regularized along the superior-inferior axis. We usually like to use SliceReg with the segmentation, just as a pre-alignment of the chord segmentation center line with the template chord center line. So You can see that as an alignment of the chord center lines, basically. If you're dealing, so another algorithm similar to slice reg would be the center mass rot, which is essentially taking the center of mass of the segmentation on each slices, and then align it with the center of mass of the segmentation in the template space. It also does a rotation in case your subject has like a turn his neck, for example, or sometimes there are compression in one side of the chord so that the chord would slightly move in the axial plane. So that algorithm takes care of this. In case of highly compressed chord, some of the regularized methods don't really work. So in that case, there is a possibility to run a column-wise algorithm that was suggested by a collaborator at University of Toronto, Alan Martin. It basically takes the segmentation and try to matches the compressed segmentation with the chord segmentation of the template. So you can see that as a nonlinear deformation with much more degree of freedom than the scene-based approaches. I know this can be overwhelming to have too many choices of algorithms, so don't hesitate to post questions on the forum if you need a bit of guidance. Another basics that is important to keep in mind also is that a registration comes with a warping field or a transformation field, and since we use partly ANTs, we are using the ITK convention for warping fields. And the ITK convention is different from the FSL and SPM convention. The warping fields are not defined in the same way. There is a way to make the warping fields compatible between FSL, SPM, and ITK by using these commands. However, I added a warning here after discussions with Joe and other folks in the community who would like to basically pre-process their fMRI data and then run FSL pipeline for doing fMRI studies. There is currently a problem when we want to convert warping fields that are not defined in the same coordinate space. It's a bit of a tricky problem. It has not been solved yet, even though a couple of people from different institutions are banging their head in the wall to trying to solve that. It's not solved yet, as far as I know, so we are working on it. And hopefully we'll find a solution soon. So, now that you've registered your anatomical data to the template, the next obvious step you want to do is to also register another image that was acquired during the same session. It could be a DTI or an MT image. And the way you do that is by registering your MT or diffusion tensor imaging or fMRI data to the anatomical data that was acquired during the same session. And then you would concatenate the warping fields between the anatomical and the template, and the metric and the anatomical. If you concatenate those two warping fields, then you have the transformation, a single transformation between the template and the metric. And since this is a bijective warping field, you also have the transformation between the metric and the template. Okay. And once you do that, you can bring the template objects, such as the atlas, the white matter tracts, inside the subject space, and then you can quantify, for example, MTR or FA in various white matter tracts. And you can also take advantage of the automated vertebral labeling, and then you can compute an average CSA at between C2 and C5, for example. Okay. And this is the kind of outputs that you would get. You get the vertebral labeling, You can compute CSA across the vertebral levels, CSA for the cord, or CSA for the gray matter or the white matter. And this is the atlas-based analysis that I was just talking about. All right. So now we can start doing the hands-on after all this theory, so we can wake up a little bit. And the first step to do is to label the discs or the vertebra. So we're going back to our T2 weighted folder. So I'm typing cd /T2. As you can see, I am now in the T2 folder. If I do an ls, I have more files. Now I have my T2, but I also have my T2 centerline as well as my T2 segmentation. Okay. So I'm going to run this this command here, and while this is running, I will explain you what it does. So the function is called SCT label vertebra. So as you know, it doesn't reach for the moon. It basically labels the vertebra. That's what it does. The input is the T2 image as well as the segmentation. Right? It uses the segmentation to basically move the window that will find the disk, that will find each disk. The algorithm works by straightening the spinal cord first, so that it makes it easy for the algorithm to do the moving windows along the spinal cord. So that takes a little bit of time. And then you'll see what it does. It does some resampling, blah, blah, blah. A very important aspect is that it runs a C2, C3 detector. So it finds C2, C3 level. Why C2, C3? Because that's the easiest point to recognize from in the spine. You know, it's difficult when you look at a spine that is somewhere in the thoracic T7 to T9, for example. If someone only shows you that, it's impossible for you to tell what level you're in, right? So a good fiducial anatomical marker to identify, to count the vertebral levels is to start from C2, C3 disc. Okay, so there is a machine learning algorithm that was trained to find this C2, C3 across different contrasts. Once the disc is detected, it basically goes down, adjusting the size, the interdistance of the disc from probabilistic information based on a collection of adult spines. So if someone is very tall, for example, then it will adjust this probability as it finds more and more discs. So it finds all the different peaks. It unstraightens the spinal cord, the labels, and then it warps the label, and that's your output. So we can open the QC report. So I'm going back to my browser, and I'm doing a refresh. And now I'm seeing my labeling here, and I can toggle back and forth, and you can see. So the contrast here is not so great. So I'm just going to zoom. Yeah, the contrast is not fantastic, but you can trust me that basically this is the C2, C3 disk. On your computer, it might appear better. Okay. If the labeling fails, you can also do it manually. You can basically run label utils and then click at, let's say, the posterior tip of C2, C3 disk, for example. So you can try that at home. Once the vertebral labeling has been done, we want to output those 2 points. And those 2 points will be used for the registration to the template. You remember there is a phase where the spinal cord is straightened, and then once it's straightened, it will basically try to match the level of your subject to the level of the template, right? So if you have someone tall or small, you want to make sure that the spine will be matched with the template, with the PAN50 templates. So one way to do that is to select 2 points, and then there is an affine transformation that is found between those 2 points. So what we will do here is, based on the labeled segmentation, which is here, T2_seg_labeled, which is output, which is an output of the vertebral labeling, which is what you see here. We're going to create labels 3 and 9 centered at the vertebral body. That's what this command is doing. So I'm going to copy paste this into my terminal window, enter, and that's it. So it recognizes all the different labels from my labeled segmentation, but it will only pick the value 3 and 9 as per my command. And it will output this into a file called T2_labels_vert. Okay. If you really don't want to bother with SCT label vertebra, you can completely bypass that and just do the labelings yourself. You can just point at C2 and point at C5, for example, and use that for the subsequent registration. So moving to the registration, this is the core command, the famous command that will enable you to register your data to the template. No mystery, it's called SCT register to template. The inputs are the T2, the segmentation, the labels that we just created, the labels at C3 and T1. We mentioned that the contrast is T2, and then we also ask to output the QC report. So I'm going to copy paste this command here, and then it will run for 1 or 2 minutes. The first, it will find all the existing labels in the template in order to match the labels that you're asking for. In that case, you're asking for labels 3 and 9. So it will find those labels in the template space. And then it will straighten the spinal cord, which is on here. And then it will create an affine transformation between the straightened cord and the template to match the different labels. And then it will do this non-linear slice-wise, like an axial, in the axial plane, non-linear registration. So the question is, what are the algorithms? You know, I've showed you a lot of algorithms here, right? Question is, what are the algorithms that are used by default? And you can have this information. So I'm going to open another terminal window so that we can just, I can just show you what are the defaults. If you type SCT register to template, enter, it shows the usage of the command. And inside the usage, you see that there is a bunch of parameters. These are the input file, segmentation, label. You can also input the disc label if you want, as opposed to the vertebral labels. Output folder, this we're going to talk about it later. But the thing I wanted to show you is the param flag, which is the most expensive flag of this command. It's a bit complicated, but what it does here is that the registration to the template is a multi-step registration. The first step is an affine transformation between the straightened cord and the template. That's called step 0. And usually you don't have access to that. What you have access to are the step 1, 2, and more if you want. The step 1 is using the image, both the image and the segmentation. Okay, that's a new feature, by the way. Before it was only IM or seg, but now it's possible to do IM seg. The algorithm is center mass rot, so it will basically try to align the center of mass and then find the cord orientation in the axial plane in order to match it with that of the template. And then there are other parameters that are not relevant with this algorithm. Okay, but it just outputs everything here. Once the center of mass are aligned, it does a second step, and in that case, we are using only the segmentation. Okay, so we are, as you see, we are relying poorly on the image in order to be robust to images that are of poor quality with artifacts and so on. The algorithm we are using here is the B-spline SIN, which is good to use with the mean squares metric. We do 3 iterations, a smoothing factor of 1 millimeter. These are parameters that are specific to ants, basically the rapidity with which the gradient descent will converge. Slice-wise is basically asking whether we want to treat each slice independently or not. In that case, it's set to 0, which means that it will regularize the deformation across the superior-inferior axis. And these fields are not relevant. Okay, so now if I go back to my other window, the process is finished. It ran in a bit more than 2 minutes. And we can look at the QC report. So I'm refreshing my QC report, and you see now that I have the function SCT registered to template that is appearing here. So if I move here, I can basically switch back and forth between my subject, which is this guy here, and the template that is registered into the subject space. Okay, so you can really inspect all different slices and how well the alignment is done between your template and your subject. You can also look at it inside Facialize by copy pasting this command, and you can also toggle with F, with Command F or Control F between the template and the subject. Okay, and you can, one thing that you want to look for also is the alignment, the vertebral alignment. So in that case, you see that the discs are well aligned. Oh, you don't see it on this screen. Sorry about that. But again, you can trust me. Oh, maybe I can change the brightness of the image. So here, yeah. Okay, you do see the discs now. Okay. So you can see that the discs are well aligned between the template and your subject, and that's the kind of thing that you want to QC for, right?
I have a question.
Yes.
You said that you have used the spinal cord template and the brain template. At what step does this make a difference?
Yeah. So far the studies that included both the brain and the spinal cord started by doing like guillotine type of action by removing the head, by separating the head and the spinal cord, and doing those two pre-processing separately. Brain data using favorite pipelines like BET, for example, for like skull extraction and things like that. And the spinal cord would be processed using SCT. And then each of the products of the two parallel pipelines would be registered to the MNI template space. And this is where the brain and the spine would join together for further statistical analysis, for example, or group studies. Okay. So that's just a GIF animation of the registration. So there are a couple of parameters in this register to template command, and it's a bit tricky to comprehend everything. So I'm going to talk about a little bit of like the important features. If you have again any questions or if things don't work as expected, just ask the question on the forum. So the flag ref is an important flag. What we did here was, so we did not specify the ref flag in our commands. The ref flag by default is template. And the ref flag can take values template or subjects. When we select the default one, which is like ref template, what it will do is that it will register, it will straighten the spinal cord of the subject, and then it will register the subject to the template. It will still generate a forward and inverse warping field, so you will be able to, to work in the template space or the subject space. But if you select -ref subject, instead of registering the subject to the template, you will register the template to the subject. And there are a couple of differences of implications. A very strong implication is that there will not be any straightening done. And the question of the gentleman asking about what's happening if you have thick slices, in which case we don't necessarily want to do a straightening, or if you acquire only like few slices in a part of the cord that you know is fairly straight, which is often the case when we do diffusion or fMRI protocols. We only image with a few slices in a part of the cord that is supposedly straight. In those cases, we might want to avoid doing any straightening, and so we can select -ref subject in those cases. So this blah blah is basically what I just did, what I just said. So the param flag, I already explained that. You have the possibility to basically bypass the default parameters. By default, it's using center mass rods. Actually, I'm going to correct it right now. And this is IMSEG. Okay, so by default, the first step is center mass rod, and the second step is the B-spline scene, mean square, 3 iterations, and and slice-wise regularization. If you are not happy with that default parameters, you can play with those. Carefully choose the type, if it's image or segmentation, and make sure to also choose the right metric. Right? If you're using ants on an image, I recommend you use cross correlation metric, which is fairly robust. You don't want to use mean square if you're registering 2 different modalities, right? It's just gonna fail. With the segmentation, use the mean square metric. It's fast and it's the correct metrics to use. There is another flag which is called -L disk. So it's fairly simple. Instead of, in case you don't have the labels at the mid-vertebral body, but you decide to have them at the level of the disk, then you should use -L disk as opposed to -L. Okay, that's also explained in the documentation here. -L would be the mid-vertebral level, whereas -L disk would be labels located at the posterior edge of intervertebral discs. Okay. Another thing to mention is that you can also select more than 2 labels if you want, or you can select one label. If you have an FOV that only shows one disc, then you can just use one label, and the registration to template will work, except that it will not do any affine adjustment, obviously, because it needs at least two labels to do that. Okay. I talked about highly compressed chords. For example, there are cases where the registration is very difficult to achieve. My colleagues in the neurosurgery department brings me a lot of cases where the chord is highly compressed, almost not visible. So they basically always fix the segmentation that usually fails using automated algorithms. And then from this manually corrected segmentation, it is possible to obtain a deformation field that's using more degree of freedom. So that's in that case we are using the algo column-wise in order to accommodate very severe, very strong deformation. Any questions so far? So what we've obtained with this command register to template are warping fields. So I can show you the warping fields here. So this is our T2 image, segmentation, and these are the warping fields. So we have a warping field to bring the anatomical image to the template, and another one that brings this one that brings the template to the anatomical image. Right? So again, you can work in both spaces. In our case, we will work more in the subject space. So the next thing we want to do is bring the template objects, the atlas, the vertebral levels, and so on, into the subject space. So to do that, we're going to use the command SCT warp template. So I'm going to run it, and then I'll explain what it does. The inputs are the T2 image, which is the destination image, the image you want to bring the template objects to. Obviously, we need the warping field from the template to the anatomic image. -A is a flag that I can show you in the usage, but -A is, if I type SCT warp template, enter, -A is an optional argument. By default, it's equal to 1, and it warps the atlas of the white matter. In our case here, at this point, we don't need this white matter atlas. So I'm just setting A to 0 because it's faster. You can also warp the spinal levels, which is a probabilistic location of the spinal roots, as opposed to so it gives the spinal as opposed to the vertebral levels, which is definitely of interest for fMRI studies. So I go back to my other window. It finished. Okay, so now we can observe on the QC report the result. I'm doing a refresh, and then that's my result. So it shows the white matter mask overlaid on my subject spinal cord. Yes, Bob?
How does it work with the warping of the spinal levels when they overlap? Do you take the spinal level that has a higher probability?
So the warping algorithm will, so the spinal level, okay, so basically when we warp the spinal levels, it will warp the spinal levels based on the known location of the vertebral levels. Okay, and then it's just one-on-one correspondence between the vertebral level and the spinal level. Yeah, that's it. That's it. Okay. So what can we do with that information? The first thing we can compute is, for example, the cross-sectional area based on the chord segmentation. But now that we have the template object, we can also interrogate, we can average cross-sectional area across different vertebral levels. And so there's a couple of options here. So the first thing that we're going to run is the command is called process segmentation. So it does a bunch of different processes on the segmentation, not only cross-sectional area or CSA, but other metrics as well. The input will be the segmentation. Minus vert means that we want to compute, we want to aggregate this CSA within the C3 and C4 vertebral levels. And minus O is the file name that is going to be generated. Okay, so it's pretty fast. That's our output. It's a CSV file. And so we can open it with your favorite CSV viewer. In my case, on OS X, it's going to be numbers. You can open it with Excel, for example. And so if we make it a bit bigger, you have a timestamp, SCT version, file name, useful things. What's relevant, so that's what you asked for, right? You asked for vertebral levels 3 and 4, which corresponds to the slices 144 to 187. And that's the mean CSA. That's the standard deviation of your CSA within those different levels. And you also have additional information such as the angle of, so I need to explain that a little bit. Angle AP and angle RL. What does that mean? These are explained here. So angle AP is the estimated angle of the spinal cord between the spinal cord. So it's basically the angle of the spinal cord in the about the AP axis. So in that case, it's the axis that that goes perpendicular to the screen. Okay, and RL angle is the angle that is about the right-left axis. Okay. Why is this angle important? This angle is important because the cross-sectional area is measured by computing the area of the mask, of the cord mask, or any mask, on a slice-by-slice basis, and then adjusting using the cosine of the angle between the slice and the actual cord center line. Okay, so if the angle is not properly estimated, the resulting CSA will be wrong. So there are a couple of options, different types of outputs. What we did here was to output the CSA like as an average between C3 and C4 level. We can also ask to output it per level. So let's say I'm running this command, and the only thing that changed here is that I added the flag minus per level 1, and it means that it will output a file, and now I'll have 2 different rows, and each row will correspond to a particular level, right? Level 4 and level 3. With the average CSA within each level and so on, okay? We can also, instead of asking to get the CSA per vertebral level, you can ask to have it by slice. So if you input minus Z as opposed to minus vert, you can have the CSA for the slices between 30 and 35, and you can also ask to output it per slice, right? So this is going to be the output. So now I have a bunch of rows, and each row corresponds to a particular slice, right? And in that case, my column vert level is empty, right? So we talked about CSA, but this function also computes other metrics that could be relevant for looking, deeper into chord shape analysis. It can output the AP diameter, the right-left diameter, the eccentricity of the chord, the symmetry of the chord, and its orientation. And Martin et al. Published a study showing that some of these more thorough metrics, like chord shape metrics, could be relevant for diagnosing chord compression, like cervical myelopathy, for example. Any questions so far? So, how do you add another contrast to the analysis? As we saw, we would basically have another set of images, DTI, fMRI, and then we would register it to our template via the pre-register warping field of the anatomical image. So we're going to do that on the MT data that is provided with the course example. So let's go to the MT folder. If I do an ls minus LA, I have my list of files. So I have an MT0 and an MT1, which corresponds to a gradient echo image without and with the magnetization transfer pulse, respectively. So we're going to segment the spinal cord using DeepSeg. So I'm copy-pasting the command here. So it finds the center line, patches, and then segmentation is done. We can check it on the QC reports, and it looks okay. Next step would be to create a mask. Why would we want to create a mask? For a more accurate co-registration between the MT0 and the MT1. You probably know that as opposed to the brain, where rigid registrations are usually satisfactory, with the spinal area, it's a bit more difficult to do a co-registration because the muscles and the rest of the tissue could move independently from the spinal cord. So if you want accurate registration between two spinal cords, even if it's the same subject, the same session, you might want to focus on a particular region. So in that case, we can create a mask around the spinal cord automatically from the spinal cord center line that is coming from the segmentation. So we already did the segmentation, so we can just run this command, create mask. So create mask is inputting the MT1 image. Minus P will be the process for creating this center line, or this mask, sorry. So in that case, we will use the center line to create a mask around the center line, okay? The size of my mask will be 35 millimeter. You can also define it in terms of pixels, for example. And the shape of the mask will be a cylinder. And that's the output file. So we can have a look at it in FSLIs, for example. So that's my generated mask. I can also overlay the cord segmentation in white. So you see that the mask is really like a circle around the spinal cord, right? So we are now using this mask in order to register the MT0 onto the MT1 image. So for that, we are going to use the register multimodal command. And I'm going to explain what are the different parameters. So the first input will be the MT0, and this is the moving image, okay? Minus D, D stands for destination. This will be the destination image. So we want to move the MT0 into the MT1 space. In order to do that, we are going to get help from the segmentation. So we can input the segmentation of the T1 of the MT1 that we've previously obtained, and then we can define a couple of parameters. In that case, I'm going to say that the first step that is going to be a single step registration. Sorry, we're going to use the image, and the algorithm will be slice reg, and the metric will be the cross correlation. We are going to use the mask in order to only do the estimation inside my mask. Minus X stands for the interpolation type, so we can choose between spline, nearest neighbor, or trilinear interpolation, and that's the QC reports. Now, while I'm reading this to you, I'm realizing that there is something wrong with this syntax, actually. I did not notice before. I'm asking for well, actually, that cannot make sense. Well, the only thing that does not make sense is this. I know, actually. No, sorry, I didn't say anything. It does make sense. So what I said previously is that slice reg is only used for segmentations, but it's not true. It could also be used for images, in fact. Right. What slice reg does is that it's just a slice-wise translation, okay, that is regularized across the superior-inferior axis. So in that case, we expect within the same session that person slightly moved, maybe sometimes ahead or something, and we just want to have an alignment between the MT0 and the MT1. So we can look at the results with FSLIs, and I'm going to pull the unregistered image. So these are the, if we zoom in, this is the MT, I'm switching between the MT0 and the MT1 reg, okay? And I'm going to pull the MT1 that has not been registered. And you see that there's a slight motion. I'm going to find another slice where there is more motion, you see. It's a bit apparent. So that's between the MT1 and the MT0. And when we look at the different registered images, it's a bit more stable. Okay, so you really want to make sure before computing metrics such as MTR that the different images that are used to compute these composite metrics are properly registered. Okay. Once your images are registered, then you can compute MTR. So there is a command here called compute MTR. It takes as an input the MT0, which has been registered, and the MT1, which is the native one. Okay, and it outputs a file called MTR. For information, there are other metrics or other QMRI techniques that could be computed. For example, there is a compute MTSAT that has been programmed recently. So yeah, if you have some features that you would like to see in SCT, but please let us know. So once this MTR has been calculated, the next thing you want to do is to extract MTR values in specific parts of the spinal cord, especially the white matter. in order to do that, you first need to register your template with the MT1. Because so far we've registered the template with the anatomical image. Now we want to register the MT1 with the template. So there is this long command. I'm going to run it and explain to you what it does. Register multimodal is not register to template. We've already run register to template before, right? So we already have a warping field that brings the anatomical image to the template. What we're going to do now, and after we can make a pause because this is the key aspect, but it requires a lot of your cognitive attention. The input of this function will be the template. And I decided to use the T2 version of the template, like PAM50 T2. I could have chosen T1 or T2 T2 star. I decided to use T2 because that's the one that looks closer to my MT1 image, right? iSeg is the input segmentation. Again, I'm pointing to the SCT dir, which is a directory of my SCT software. It's installed there, /data, PAM50, and then PAM50 chord. Chord is the segmentation of the chord in the PAM50 template. Okay. So these are my two inputs. And -d is the destination. So I want to register my template to the MT1 space. So -d is my MT1 image, and -dseg is the segmentation of my destination. So MT1_seg. Okay. So far, so good. Oops. -param, I want to tweak the input parameters a little bit. What I'm going to ask for here is, for the first step, I'm going to use the segmentations. Okay. I'm going to use the center mass algorithm. Why do I do that instead of the center mass rot, for example? Because in that case, we are going to register the template, which is already pre-registered inside the anatomical space. So we do expect that if someone has like a, a turned spinal cord, it would appear turned both in the T2 and in the MT scan, right? So we assume basically a coarse, a rough, similar positioning of the patient inside the scanner. The second step will be using the segmentation as well, the B-spline scene, and we'll use a slice-wise algorithm with 3 iterations. Okay. We are going to restrict our algorithm inside the mask that we previously estimated. And an extremely important parameter here is the init warp parameter. This init warp tells the algorithm that we are going to use an initialization transformation, an initial transformation. And this one is, you see that I'm pointing like /T2. I'm going to the T2 folder that has the warping field between the template and the anatomical image, right? So I'm taking transformation between the template and the T2. I'm bringing my T2, my PAM50 T2 image inside this space here. And then I'm going to do my registration between that image and my MT1 image, which are already fairly close. And that will output, I can show you what will be the different outputs. It will output warping fields between the PAM50 T2 to the MT1. Okay, so that's my warping field to bring me from the template to the MT1, and that's it actually. That's the only warping field that is output. So now you can ask, well, what if I want to work in the template space, for example? I would need a warping field that is a warp_MT1 to PAM50 T2, right? If you want to do that, then I'm going to do -H here to get the help. and shows you that we've run the init warp. That is the initial warping field. It is the forward warping field. If you want to get the inverse warping field to go from the MT1 to the PAM50 space, you would need to also use the init warp in warping field, right? And that's going to be your T2 warp, T2 to template, or ANAT to template. Okay. So I hope you're still with me. We're just going to do those 2 slices, and then we're going to do a break. Okay. So that's just a slice to explain how to do a registration to a template when you don't have any anatomical image, because here what we've done was to use an initial warping field between the PAM50 and the anatomical image. You can also, if you don't have any anatomical image and you just have an fMRI scan, for example, you can still register it to the template. In that case, you would label your image. You need to tell the algorithm at what level you are, okay? And then you will run register to templates. Same input, your image, your segmentation, your label. It could be disk or it could be a vertebral level. In that case, you do a ref subject, okay? If you have 6 slices, for example. You can tweak the parameters or you can use the default one, and that will give you also a warping field that can bring you from the template to your MT1 and vice versa. And very last step, once you have your warping field, we're just going to rename them to be more convenient. Instead of having 3 kilometer long file names, we are going to call this one template 2MT. Okay, so I'm copy pasting my command here, and then we are going to rerun the same command as we did before, warp template, but in that case, I am not going to do -A0 because I do want the white matter atlas. So it first warps the template, and then it warps the white matter atlas. So the 30 different tracks, actually 36, they are going to be warped inside my MT1 image. And we can do a quick facilize checkup, and then we can do a break. So that's here I have overlaid a couple of images. I have in blue it's the white matter, in yellow it's the gray matter, and the T2, the PAM50 T2 template is here. And you can see that we can basically toggle on off the white matter mask, and the registration is fairly good. So at this point, you will be able to interrogate, different tracks, different metrics in different tracks in your MTR data. Any question? So I think it's a good time to take a break. Let's take a 5-minute break, and then we gather back at 5 p.m. If you have any questions in the meantime, yes?
Excuse me. So it's about a question about our data set. If we have the scan, it's a sagittal one, but
yes.
the axial slices are only for specific segments.
Yes.
Can we still use, say, the prop seg function?
So if you have...
So you have a sagittal scan of the whole cervical and upper thoracic floor, but the axial is, for example, a couple of sizes for the C2, C3, C4, C5.
Yes.
Can you still, so if you use, for example, a function like the prop seg function for only those
Sure. Yeah, you can, if you have only like say an axial acquisition that spans C3 to C4, you can still run PropSeg or DeepSeg on those, which is what we did here on the MT scan. So I can basically, if I run FSL eyes, MT1, and then MT1 seg. So here we only have, so it's more than, okay, so let's say we are spanning 5 levels. But if you have only like there to there, you can still run PropSeg or DeepSeg.
Still you need to mark the
So it depends. If you have the labels, if you have the vertebral labels from your let's say your sagittal scans, then you can use those labels for the registration to the template. If you don't have that sagittal scan, then you will need to know at what are the labels in your axial slice. So there are different ways to do that. Either you see the disc in your image, and then you can basically point it, for example, or you can also use a command called SCT label utils. And there is something called create seg, okay? And with create seg, you will create labels along the spinal cord segmentation. So instead of doing it manually, if you know, for example, that your FOV is centered at C2, C3 disc, then you can run create seg and then -1, 3, -1, 3, which says that if C2, C3 disc is centered in the superior and inferior direction in the FOV, it will create a label with a value 3 in the middle of your segmentation. And then you can use that label to do the registration to the template.
Remember, I work on neonate data. Okay.
On which?
On neonate.
Ah, yes, absolutely.
Okay.
Yeah.
And I've got problems also with segmentation because with DeepSeg I managed and the viewer, but I realized later that it takes some TFF. So I wanted some suggestions also because apart from the segmentation, there is also a problem on definition of ROI later.
Right.
Because my aim is computing average CKI matrix in white matter graphs. Okay?
Right.
And yes, I have problems with the registration of the template.
Right. So the best way is maybe you can send me like 1 or 2 representative data.
Okay.
And then I can see what solution, what's the most automated solution that I can find for your data.
I've tried with this case with radius by reducing them, but it also depends on the time.
Yeah, no, but I will try to basically smooth along the center line to improve
yes,
the
because
contrast.
that's the first time I heard about smoothing before.
Yeah. So
yes.
yeah, I will try that. So send me 1 or 2 example data and I will try
If you want, I've got them here, but I can send.
It will be. My to-do list is organized through my emails. So if you email me that, I can prioritize things. Because if you send it to me now, I'll forget.
No. Yes, okay. Perfect. Thank you.
Perfect.
A quick question. For running deep, like how much memory is recommended? I'm a doctor.
Right. Yeah, DeepSeg is the most aggressive one in terms of memory.
Yeah, so,
so usually with the run. So first of all, it depends on the size of the image. So there is no single answer. There is no single answer actually. It depends on the size of the image. It also depends.
We have a GPU. You can make the GPU send it to the GPU.
No, it's running through the CPU. Yeah. How much RAM do you have? Oh, you're using a virtual machine. Try to run your virtual machine. Try to increase the RAM.
Yeah, I have like just done the 2 GB as was recommended in the.
Yeah, but we realize that we need to, because it depends on the image. So try to increase it as much as possible. And if it still does not work, let me know, and then we can add a patch to SCT so that it will not convert to a floating point of 64. Because currently we are changing the quantization of the input image to a very large number, and blows the RAM. So we can change that to accommodate some other configurations. So let me know.
Have you looked at, the degree of chord deformation in flexion and extension positions of the neck?
I'm sorry?
Have you looked at the amount of chord deformation, change in AP diameter that happens in flexion and extension?
You mean
when patients are looking at the neck
right.
and the neck extended, is there a substantial change in the AP diameter?
Yes, there is, which is why I always recommend some positions subject to the same way across all longitudinal studies, because that has an impact in the cross-sectional area.
And is there a way to quantify that? Because actually, I'm interested in looking at the degree of information.
Yeah, it's a good question. Actually, the one way would be to look at spinal cord specific markers, like you look at the cervical enlargement, for example, as a way to position yourself always the same way, right? Or the frontomedullary junction, even though it might not be the same way as down the line.
You and I can
That's a very good point.
So, you mentioned the radial diameter, see what is the variation that happens with different positions, different dimensions. The reason I'm asking is, what happens to some patients are symptomatic and in specific position, like a compressive myelopathy? Yeah. Some patients are symptomatic, and sometimes in neutral position it looks fine, but they're really symptomatic. And when you do a flexion extension MRI, you do a dynamic MRI, you can see the degree of compression on that. But in a way, it is useful to sort of quantify that, and also in people with tether cord as well. We don't know. Because we follow them up to become symptomatic at a certain age. That's because as they grow longer, the skeleton goes longer, and then the cord really flattens. It's quite a way to say, you're symptomatic because of this and not because of something else.
Yeah, so this is an extremely good point. Yeah, thank you. So how do you enjoy it?
Thank you very much. Thanks for the invitation. If I could need anything.
Thank you very much. Same for you.
Thanks. Julian, I have some bad data to show you. Right. So I randomly picked a subject, and I didn't know if it was going to be good or bad, or so this one is actually it's the worst. It's like I picked the best worst case scenario. So there is. Yeah. So that's it's a high resolution situated sagittal. What you use So actually, I just got this phone. To be totally honest. So I was finally able to get yeah, I think it's happy. So I just
What's the thickness?
It is 2 so what I've done here is the only purpose I have for this is to
Okay, so
Brand new installed process. I haven't looked it up yet. So I called. Yeah, you're active.
oh, that's why. That's why. Okay, okay.
Yeah, I called virtual box functions from inside.
Can I use the terminal? So, millimeter. What's well, let's just start with one by one.
I'm actually
keyboard is different.
Yeah. Oh, exactly. Because they fix it. Yeah, exactly. They fix it. It's no more the butterfly. I know. Yeah.
I got mine a few months before the release. So yeah, that's not okay.
I use like MRI or
working on it.
So yeah, we just need to do that.
Research.
I think you know what?
There's a difference between the two.
So yeah, let's look at it later. But I think I have a good solution for it.
Okay, thank you.
What's the stretch for the
What's the what? Sorry.
What's the stretch for
The threshold
for the patients with the interpretation?
Yeah, it's so the white matter mass is not, so it's a soft mass that we output. For linear interpolation, it's 0.5.
Yeah,
It's finalizes
It does not binary. So actually, we recently. You know what? I'll mention it because it's relevant information. Right? Should we start again? So I have a question about, we warped the object from the template into the empty space. And the question was, what's the interpolation methods and thresholding and stuff like that? So first of all, that was our command for warp template. If I do -h to get the help, see that there is, oh, there's a flag for the interpolation method. Interesting. Ah, yeah, I know why. I know why. Okay, so let's go to the empty folder. So that's my empty folder. You see, I have all my warping fields. I have a label folder that has been created. In the label folder, I have my template folder that has all the PAM50 objects, like the T2, the T1, and so on. And there's an info label file that I'm going to explain in more details later. But this file includes masks, images, and so on. So the images are interpolated using linear interpolation. The binary masks are interpolated using nearest neighbor interpolation. And the probabilistic masks of white matter and gray matter are interpolated using linear interpolation. You also have another folder called Atlas that has all the different white matter tracts, and these are soft masks. So they are coded between 0 and 1, and it corresponds to the partial, it has the partial volume information about the tract location. And we use the linear interpolation here. All right, so now we're going to talk about gray matter segmentation. A little bit of theory. So SCT features a deep learning based method for gray matter segmentation called SCT DeepSeg GM. It's using a particular CNN architecture called dilated convolutions. You can find more information in Christian Perron's article. The pros of this method is that it's highly accurate, robust to pathologies, because we've also trained the model with different pathologies. The cons is that it's restricted to T2 star-like contrasts. So if you try using this algorithm using PSIR images, it will not work out of the box. You will have to change the contrast and so on. The older methods, SCT segment gray matter, which was based on another approach, like an atlas-based approach, is no more available. It's no more maintained. So that was it for the very quick theory. We go back to the hands-on. So we go back to the, we go now to another folder called T2S folder that encloses a T2 star weighted image. It's a multi-echo, gradient echo axial image. Okay. And now we're going to run DeepSeg. So SCT DeepSeg GM this time. -I would be my input. It's a T2 star weighted image. Oh, sorry about that. First we run the spinal cord segmentation, because we'll need that later on in order to subtract the spinal cord from the gray matter segmentation in order to get the white matter segmentation. So first we run DeepSeg SC. -I will be my T2 star weighted image. We need to specify the contrast. It's a T2 star contrast. And I'm outputting the same QC folder, QC_single such. Okay. Same as before, finds the center line, does the patch-based analysis. We can look at the QC, refresh, and that's my chord segmentation. Oops. That's my chord segmentation on the T2 star weighted image. So now we're going to run the DeepSeg algorithm. And you can see that with DeepSeg, you don't need to specify the contrast. you don't need to specify the -c parameter. This one features a fancy progress bar as well. Okay, it's done. So now we can look at the QC. And that's our gray matter segmentation. So you see that in slices where there is no visible, meaningful gray matter, it just does not segment anything. That's how the model was trained. Now that we have the spinal cord and the gray matter, we can subtract those two. And we do that using a command called SCT math that does a bunch of mathematical operations. And in that case, we want to subtract, the input will be the segmentation of the cord, and we subtract the gray matter segmentation. And we output this into a file called T2S_WM_seg, which stands for white matter segmentation. It runs pretty fast, and then we have our white matter segmentation. And we can look at it. And this is supposedly more accurate than the warped template, because this is really based on your subject's gray matter shape, which might differ across subjects, right? So we can toggle on and off the white matter. Okay. So now that you have your gray matter and white matter mask, one thing you could do is to account for the white and gray matter segmentations during template registration. So far, we've registered the template without accounting for the gray matter shape, but we could do that in principle. So there's an additional step here in purple, which we will follow. We will use register multimodal, the same command as before, with the initial warping field, which is the T2 warp template to ANAT. So we'll bring the PAM50 into the T2 space image. And we also include the inverse warping field, because we will want to generate the forward and as well as the inverse warping field. And in that case, we will register, we will use the segmentation, as you can see, type equals seg. And we will use the PAM50 white matter mask that will be registered to the white matter mask of the subjects. Okay, so we'll basically do a white matter based registration that is supposedly more accurate than the spinal cord segmentation. So I'm going to copy paste this command here. So it's, as you see, it's a slice by slice registration. And it's using ANS registration. So you have really the full verbose of all the commands that are run. And so if you want to debug or try things, you can always go into the temp folder, which is indicated here, and then run any of those binary commands here. Okay, it's almost done. It's done. Okay, so it created a QC report that we can look at, refresh, and then it did register of the templates in that case, the T2 star version of the PAN50 inside my T2 star weighted image. And obviously, you could do the same if you have fMRI, like gradient echo EPI scans, for example. That's the kind of contrast that you would do, for example. So now I'm going to rename the warping fields for clarity. And then warp my template objects into the T2 star weighted image. The reason I want to do that is to have the vertebral level information from the templates into my T2 star space. And so while this is running, I can go to the next slide to show you what we're going to do next. We're going to compute the cross-sectional area, not of the spinal cord, but of the gray matter and the white matter specifically. Okay, so we are going to use the same command as before, process segmentation, but instead of inputting the T2S underscore seg, we're going to input T2S underscore GM seg, which stands for the gray matter segmentation. And we're going to do the same for the white matter segmentation. There is a little bit of like some information that you need to know here. I've used a flag called -angle core 0. Does anybody have any idea what that means? What's that used for? Why do we use that here? So, as I mentioned before, the cross-sectional area is computed by adjusting the angle of the chord center line based on the slice, right? In some cases, you might not want to do that if you are not sure about the proper estimation of the center line angle, or if you're sure that you positioned your FOV or your slices like very well or orthogonal to the spinal cord. In that case, you could switch off the angle correction, and the cross-sectional area that you're going to measure is going to be exactly basically the weighted sum of all the pixels in your masks. So we're going to run those two commands here. Copy and paste. And there are two outputs that I'm going to show you here on my Finder. So I go to the T2S folder, and there are those two CSV files that have been generated. And if I look at them, it looks a bit overwhelming, but it's similar to before. You have the timestamp, SCT version, file name, which in this case is the white matter segmentation. Each row corresponds to a slice, and then you have the mean, like the mean cross-sectional area within this slice. So you see that some slice shows none. The reason it shows none is because the gray matter was not segmented in some of the slices because of poor image quality. So if that happens, then you just get a none. Okay. If you have registered your template using the gray matter shape information, what you can do is improve the registration of other metrics. Let's say if you have a MRI or MT scans, you can now take into account the gray matter shape for your registration. And so we're going to do that here. We go back to the MT folder, and we're going to run register multimodal. So I'm running it, and then I'll explain to you what we are inputting in the command. So the input will be the T2 of the PAN50. So it's the PAN50 template, as well as its chord segmentation. The destination image is the same as before. It's the MT1. and its segmentation. The rest is also similar to what we have. What's changing here is that the initial warping field is no more the T2 warp template to ANAT, but it's the T2 star warp template to T2 star. Okay, so we are basically using another warping field that is slightly different than the one that we generated for the T2 image, because this one does take into account the gray matter shape. Okay. And this is the results. We are going to rename the warping fields for clarity, and then we can warp the templates. So now the question that you might ask is, what if I don't have a T2 star weighted scan in order to do an accurate registration of the template? So the answer is, don't worry. We've tried in various subjects, and in fact, there is fairly small variation of gray matter shape across subjects. It does exist, there is one, but in most of the cases, it's submillimetric. So even if you're dealing with metrics with a coarse resolution, and if you're integrating the metrics across different slices and tracts, that lack of gray matter shape information will not affect your metric extraction very much. That's the message. Okay, any question so far on the gray matter segmentation? If not, we can move to the another exciting section of the course, which is atlas-based analysis. So now that we've done all those registrations and warping template and so on, we really want to get our results out. And this is how you get your results out. So a little bit of theory. The atlas-based analysis uses an atlas. This atlas is generated from the Gray's Anatomy white matter tracts, and you can get more information on Levy et al.'s paper. We digitalized the gray matter, the Gray's Anatomy atlas into all those different tracts, so 30 white matter tracts and 3 × 2 gray matter tracts, as well as the surrounding cerebrospinal fluid. Something to consider when you do matrix estimation is that your MRI scans is like a discrete space. So you're basically sampling your spinal cord with coarse voxels. And what you want to get is not the value inside the voxel, but ultimately you want the value inside a particular spinal cord tract, right? You don't know that. What you know is the value that your voxel gives you, right? So if you look at the voxel that is at the periphery between the white matter and the cerebrospinal fluid, and assuming that the value in the white matter is 50 and the value inside the cerebrospinal fluid is 0, the voxel will give you the value 25, right? So now if you use binary masks, you're stuck with that, right? You won't be able to retrieve the actual true value inside the tract. But the beauty of using partial volume masks is that we are able to retrieve that information. So the true value inside the subpixelar masks using Gaussian mixture theory. And there are different algorithms to do that. There is the maximum likelihood or the maximum a posteriori. And by default, SCT extract matrix is using the maximum a posteriori approach. And that requires to have all the different white matter tracts that are registered in your image. And then it will try to estimate the value. So it's basically like a grading problem. So we have a lot of voxels that are listed in Y, in the Y variable. and what you want to estimate is the beta. And the beta is the true value within each of the tracts. So it's a linear process. We assume some noise. We assume constant homogeneous values within each tract. That's an assumption that we make. Okay. And through that algorithm, you can estimate the true value within tracts. So we've done a lot of validation by looking at different levels of noise, different tract size, different image resolution, different algorithms, and so on. So the take-home message here is that the maximum a posteriori is the most robust to noise in order to estimate the tract value inside the spinal cord. Again, you can get more information about those validations in those two papers. All right, so let's move on to the hands-on part. I already told you about this info label file. That's a critical file that is located into the label atlas file that is generated by the warp template. So if we go to the empty folder, the label folder has the atlas folder, and that has all the tracts as well as an info label file. This info label file has all the different white matter tracts that are labeled with a different ID and also a name and the file name. And if you go more down, you'll see that there is a combined label section. The combined label is something that you can use if you want to compute, for example, MT value within the entire spinal cord. You would use the label 50. If you want to compute within the white matter, you would use label 51, 52, 53, and so on. And you can see that this spinal cord, the white matter, and all those combined tracts are basically a combination of all the individual tracts that are listed here, right? So I've got a couple of requests of people wanting to compute metrics within the left white matter tracts, for example. So in that case, you could easily edit these info label files and then add your custom combined tracts. You can add 56, comma, left tracts, comma, and then you can basically put the numbers of the tracts that corresponds to your left white matter tracts. So you can do all the custom combinations that you like. And this slide is exactly what I was explaining. So this slide now explains how to do that. Maybe I can add a little bit of information. If you have the choice of editing this info label file, right, which has been created by SCT warp template, right? So you can edit it. I can open it, and I can say, 56, comma, my awesome tract. And then you would put the numbers, 3, 5 until 7, and so on. And then you can save it. I'm saving it. But then you have another subject that you want to process, and then you have to do the same again and again for all your subjects. If you want to avoid doing that for all your subjects, you can also, instead of editing this info label, you can edit the source info label, the one that is copied by the function SCT warp template. And this one is located in the SCT installation folder. So in my case, so you can see where SCT is installed. You can do echo SCT dir. That's the variable we've been using so far. SCT is installed here in my case. So I'm just going to go in this folder, code SCT data PAM50 atlas info label. This info label is the one that is copied every time you launch SCT warp template. So if you modify this one, then it will use this one every time you run the warp template command. Okay. All right, so now we can use SCT extract metric, and we're going to do that together. So I'll explain why I'm running this command. SCT extract metric. -I will be the image, the nifty image that we are going to use for the metric extraction. -method is the method that we want to use. MAP for maximum a posteriori. -L is the combined track that I want to do. So I'm going to use 51. And -O is the output file that is going to be generated. So mtr in white matter.csv. Enter, loads the matrix, and then it outputs the CSV file. Then we can open this CSV file. And you see that similarly to the process segmentation, it gives a timestamp, file name, and for each slice, you have the value of the, sorry, it's going to be here, the MTR value. So in slice number 1, MTR value is 56, 41, 55, 52, 53, and so on. Okay. It gives the standard deviation. And it also gives, that's an interesting column here, it gives the size of your ROI, so the size of your mask, which was used to extract the metric. It's in voxel. So if you look at this slice, for example, the MTR was 56, and it was estimated from about 90 pixels. So it gives you estimation of the confidence for your MTR estimation, right? If you have a lot of noise and your number of pixels is small, then you might want to consider how accurate and how precise your measurement is. Right? Now it kind of shows those parameters, you know, under the hood. But if you type -H to get the help, it explains, you know, how I chose 51. You know, it corresponds to the white matter. The method flag is also explained here, so you can choose between all those different values. -L is the label, so 51 in our case. We can append the values in the same CSV file. Yes, Ferran?
This thing of the voxels, how you can report of a variable that is displayed like the voxels percentage? Is that the partial volume of the segmentation?
It is.
It's saying size, and the unit is voxels.
Correct.
And then the voxels in the image is 1 or 2 or 3.
Yeah.
And not 2.57.
So I see what you mean. We are dealing with soft masks.
Okay.
So it's a partial volume weighted mask.
Okay.
Yeah.
Let's go to clarify for the people.
Absolutely. Yeah, good point. And similarly to the process segmentation, you can also output this based on different vertebral levels. So you can output MTR across C3 and C5, for example. You can output it per vertebral level or per slice, and so on. And that's what we're going to do here. Using the same method, now we are going to compute MTR within the left and right corticospinal tract between the slice number 5 to 15. So let's do it here. Okay, so that's the output. And this is an aggregated value between, like within 10 slices, right? Between 5 and 15. So obviously the number of voxels increases a lot, right? It increases about like tenfold compared to previously. So now we have much better confidence in our estimate of the MTR. And what's interesting to note is that the left and the right corticospinal tract give very similar MTR, which, you know, is comforting because this is a healthy control, and we would not expect the right and left corticospinal tract to be drastically different. Yeah.
What's the standard deviation here?
The standard deviation is calculated. It's the standard deviation. So because the maximum a posteriori, as you probably remember, does not output any standard deviation because it's an exact estimation of this Gaussian process. So previously we had a 0 here, and we had a lot of users being a bit confused by this 0 and reporting 0 in results, which is wrong. So now we are calculating the standard deviation within the weighted mask, and that's what we report here. Yeah. So yeah, this is another approach. We don't need to do it. I think you understood the concept. And we can also, what we've done here is that we used this soft mask coming from the white matter atlas. But if you have your own mask, let's say you want to draw a particular ROI somewhere and you want to extract metrics inside this ROI, you can also do that. And you do that by specifying the mask you want to use using the F minus F flag. Okay. Any question? So if not, we can move to the diffusion weighted MRI. So diffusion weighted MRI scan is, so I'm going to go there, is by default, by definition, a 4D scan. So it's four-dimensional file, four-dimensional nifty file that we can open, so you can have a look at how it looks like for those who are not familiar with diffusion MRI. So the first scan, the first volume is usually what we call the B0, or it's a T2 weighted scan without a diffusion gradient. And then you see that there is a volume here on SSL eyes, and we can move across different volumes. And each volume corresponds to a time point with a specific diffusion weighted gradient that is applied in a particular direction in space. That's why it's switching from like bright white to almost nothing, salt and pepper, depending on the direction of the gradients, right? So with DTI, we basically take all those images, register them together to make sure in case the patient moved during those several minutes long acquisition. And then we can estimate a composite score using a particular model, such as the diffusion tensor model, for example. So first, we are going to average all those MRI data across time. So we use SCT math for that. And then we're going to average across the temporal dimension, which corresponds to the fourth dimension. And we're going to call it DMRI mean. And you'll see that this DMRI mean is a bit more like, let's say, looks nicer than each of the individual temporal time point, because the spinal cord is much like better described, and we are going to use that for our processing. So the first thing we want to do is segment the spinal cord on this mean diffusion weighted MRI scans. So we're going to launch PropSeg. Which is very fast. We can open our QC report, and this is our DWI mean with the cord segmented. And then we create a mask around the cord for the sake of basically computational time, because we are going to crop our diffusion weighted scan using the mask. So now if I'm opening the DMRI crop, you'll see that it looks much smaller than the other one. So that's my DMRI crop. So we've basically cropped the scan around the spinal cord, and we are only going to keep it and to process this one for motion correction, right? Because we don't need all the crap around it, right? Just takes space, time, it's useless. So next is the motion correction, and it's been highly inspired by Gordon's work here, who is actually here. So he did some work on the ways to basically propose a group-wise motion correction algorithm and increment also the targets which is used for the motion correction. This algorithm, this DMRI MOCO algorithm, also uses the slice reg algorithm, which I told you about, which regularizes all the XY translation along the superior inferior axis. We can also use a Gaussian mask in order to concentrate the estimation of the transformation matrix inside the spinal cord. There's an outlier detection module as well. So passing all the details, the command looks like this. And there's a bunch of parameters which I'm not going to dive into, but if you have any specific questions or if your motion correction does not work as you expect, then please let us know, and then we can try to see how we could improve things on your end. Yes?
Just a general question, Julian. When you show the results in the table, it has like a lot of decimal places. Do we know how many significant digits the results have, and like when we report, what's the appropriate numbers to report?
Well, that's not a question for me. It's a question for the reviewers.
Fair enough. But I mean, I guess what would the inherent accuracy if you, if you say what's the area of a slice and it says, to 20 decimal points. Like.
Yeah. So I mean, the nerdy answer would be that the results are long float 64 quantization. So it's highly precise, and you probably don't need that precision. I really don't think I can answer that question, because that will depend on your effect size you're looking for. If you're looking for infinitesimal effect size of 0.0001, then you probably want that at least that precision. If you're comparing apple and bananas, like FA in between apple and bananas, you probably don't need that precision. Yeah. So a good QC. So it's not straightforward to. So there's no a single way to do QC of motion correction. And so Gordon also touched base on that during the meeting today. But what I like to do is basically look at the video of the different scans. So I would basically launch this this video. We can increase the brightness a little bit, and then you can check across different volumes if your spinal cord is basically stable in the XY plane, and you can do that across the different slices, right? So once you're happy with your motion correction, the next step is to register your diffusion weighted scans to the template. So first we're going to do a segmentation of the cord on the motion corrected data, because previously we did it on the non-motion corrected data. So we run PropSeg on the DMRI crop MOCO DWI mean, which is the average, the DWI averaged of the motion corrected data. And then we register to the template. So again, we are using the register multimodal command because we already have the initial warping field, which is here. You see, we are using init warp from the T2 star scan. So you remember we did a pre-registration of the template to the T2 star image, accounting for the gray matter shape. So we are reusing that warping field. We did use it for the MT scan, and we are reusing it for the DWI scan as well. Okay. So this is done. So now we can rename our warping field and warp the template object to the DMRI space. And while we do that, we can also look at the QC report. The QC report shows the result of the registration of the PAM50 template to the DWI scan. Now that what you notice here is that we registered the T1 version of the PAM50 on the DWI scan. Why did we do that? Because the T1 weighted is contrast that is closer and closest to the mean DWI scan, right? Whereas for the MT case, which is here, we used the T2 version of the PAM50 template. So here's the T2 PAM50, and this is the T1 PAM50. Okay, so if we refresh, okay, I didn't do any QC report here for this command. I guess we can remove that, or maybe what I can do is just I can fix my thing here, QC minus QC single sub. So I'm editing the course material on the fly. Then I'm just rerunning it. So now it will generate the QC report. Okay, so now we can go back to the QC report, refresh, and now we have the warped template on the DWI scan. So, yeah. Okay. Gordon, what I'd like the issue that you showed this morning, I suspect was related to this step, which for some reason didn't work as expected.
I thought about it. I think the root cause is they're not taking care of the distortion in the device scan.
Yeah, it's possible.
Because there's the edge box, so there's slight mismatch
Yeah.
across the DWI volumes.
Right.
And we are using the mean.
Yeah.
And the non-linear registration is doing as best as it can, but you can never take account of those slight distortion across the edge box.
Yeah.
So you always have those edge box, so
yeah.
kind of not taken care of in the LMS and that.
Yeah.
Bias.
So you'll receive an email from me, and we can work together on how to tweak this registration steps. Yeah. So now that you've registered your template to the DMRI space, you can compute DTI metrics, which is done using SCT DMRI compute DTI. And for full disclosure, this function here is using a Python package called DiPy, which is developed by a very active group, and we are relying on this great Python package. I should also mention that we are relying on another very active package called Nibabel, which is used for reading and writing Nifty files. So now that the DTI images have been computed, we can then extract the matrix. But before doing that, I just want to comment on the matrix computation. And it was actually one of my questions for Gordon this morning, which I now have the opportunity because I'm the only one talking, so I can say whatever I want. So talking about the method for computing the diffusion tensors. So we used by default the standard method, but there is an algorithm that was proposed by Derek Jones called Raster, which takes care, it's basically a robust fitting approach with outlier detection. So I was wondering if to basically account for the outliers in the time series. So it's great to do QC. I strongly encourage everyone to do QC, but to instead of manually discarding those programmatic slices, if like other algorithms, other fitting algorithm could also be used, potentially giving it less variability in the matrix. Or
yeah, you should take out the large signal data.
Yeah, but it's true that if half of the images,
a hole in the image, then now they will take out.
Yeah.
How do you weight the metric, the cost function? Is it?
You mean in the Raster algorithm?
Yeah, in the Raster.
So it's the implementation from the DIPI folks. So I haven't looked deeply into that, but there is an estimation. I should probably. Yeah, I don't want to say stupid things, so I'm not exactly sure. I forgot what's the exact implementation.
I just used the average residuals in the entire core mask in my original paper.
Okay.
Sure,
yeah,
there might be smarter ways.
We can look into that, but my experience is that it does deal pretty well with a few outliers. But obviously, if half of the images are like dark or like artifacted, this is not going to work very well. But it's just for information that there is this possibility to use another algorithm.
Well, I think if it works well, definitely it should be the default.
Yes, it's just longer to run, and some people also don't mask out the image, so it might take a lot of time to do a pixel-wise analysis.
It will be easy to implement the weighted cost function just as you mask.
Yeah, it's true. But yeah, the default is the standard equation without fancy regularization. Okay, so we are almost towards the end of the course. Maybe let's take an additional 15 minutes to talk about some of the features that could be of interest. The first feature is, we've talked about it already, is the QC, the quality control. We are constantly improving it and adding functions to it. So you're encouraged to use that QC module. One advantage of the QC module is that, as you saw, it generates an HTML file inside a single folder. So this folder is here, and inside this single folder, I have all my QC that is shown in my browser here. So if you want to share your QC reports with your colleagues, or if you want to publish and also join the QC report along with your publication, you can easily zip that folder and then ship it. It's only a few megabytes. So that's a useful feature. Another feature is the FSLI's integration. So I'm going to do a demonstration. You can call FSLIs. And then you can run the script. which is called SCT plugin, and it's located under your SCT installation folder, contrib, Facel integration, open, and then it opens an SCT panel. So currently there are only two panels, SCT DeepSeg SC and SCT DeepSeg GM. So you can open an image, let's say an empty by empty one image, and then we can run DeepSeg. So you select the contrast, spinal cord segmentation, and then it shows the overlaid segmentation directly inside the window. So it's really like a GUI-based SCT, right? So we are currently working a lot, trying to add other functions to it, and to actually, let me take 1 minute to show you that very, very soon there's going to be a lot of other functions to it. If I go to my specific branch, Facelize, I'm taking a lot of risks here, doing that on the fly. I hope there won't be any bugs. We'll see. Run script. Okay, so you see that now there's much more functions that are covered. PropSeg, label vertebra, register to template, process segmentation, motion correction, and so on. So this will be coming up very, very soon. Stay tuned. There is also web tools that Ferran has put together via the Nifty Web platform. So it's like basically go to the website and you can upload an image, and it generates the segmentation on the remote server, and then you can download the segmentation. So it was kind of a proof of concept for a web-based platform. Another feature, if you're having some segmentation problems on images, and so Rob, that's the feature I wanted to try on your data, is to smooth along the spinal cord. So you can basically, let's go on the T1 weighted image, and then you input the segmentation of your image, as well as the image itself. And it will run a smoothing kernel along the spinal cord center line. So now it's a chicken and egg problem, because in order to get the smoothing, you need the segmentation. So the plan is to get a kind of a coarse segmentation that looks a bit ugly. This input segmentation is basically used to generate a spline function. So it's an extremely smooth function that is used for the smoothing kernel. So it doesn't need to be a perfect segmentation, just something, following the spinal cord, sort of, and then it will straighten it, smooth along it, and then straighten the image, and then you get a smooth version of the spinal cord. And once you have that, you can rerun the segmentation, and hopefully it will work much better.
Do you need the center line for that?
The center line or the segmentation. It's usually better to input the segmentation because you have a more precise definition of the center line.
Yeah, because the DeepSeg doesn't output it.
Correct, it does not. So you can just input the segmentation.
Okay.
Yeah. Yeah. So let's just have a look at the output. Yeah. So now we can compare the T1, like the native T1 image. Oops. So that's the, well, it's not very clear. Okay, so that's the native T1 image, and that's the smooth version. So I'm switching between the two, and you can see that it's basically smooth along the chord, but not, you still conserve all the different boundaries. You can also, if you want to generate pretty pictures, you can flatten the chord. So basically align the medial plane of the chord inside a single 2D image. That's the flatten sagittal command. We talked a little bit about spinal labeling. It's a probabilistic location of the spinal levels that are based on the vertebral levels and the manual identification of the nerve roots done by a neuroradiologist, David Cadot, who was at U of T at the time. He did it in 20 adults, and so we used that results to generate these spinal levels. So that could be used for spinal cord fMRI results. And so I'm not going to go into details here for the sake of time, but you can try to run those commands in order to register the gradient echo EPI data to the template, and then warp the template as well as the spinal level, which is indicated here with the flag -S1. Then you get not only the vertebral level, but also the probabilistic spinal level. A couple of comments, like don't hesitate to look at the help of different functions. SCT image is a generic function to manipulate images, change orientation, pad, things like that. SCT math is the little sister of FSL math. It does pretty much the same things. So this we don't need to mention. And the very last point I want to show you is I think extremely important. It's about batching. So we talked a lot during this workshop about reproducibility of results. If you type sequentially those commands in your terminal and then generate results and then publish your article, 6 months after that, reviewers will ask you to regenerate or to change a slight thing in your parameters, or your boss might ask you to regenerate those data because the hard drive has crashed, for example. And in order to be able to regenerate everything based on the input data, you can only do it if you batch your processes. So you can create what we call the batch script, for example, which looks like so SCT course single subject. So yeah, which looks like this, right? So you have basically a sequential amount of commands that we followed so far during the course. In order to process multiple subjects, you can also use the same script and then loop across, let's say, 5,000 subjects, right? And so you basically create this batch, and then you can run an SCT command, which is called SCT run batch, that points to a parameter file, and then a batch script that's where you list all the different commands that you want to run for each of your subjects. And then you grab a coffee, you go to the movies, and you come back, and your 5,000 subjects are processed. And the beauty of this is that 6 months from now, you can basically rerun this single command and obtain the same results again. So I strongly encourage everyone to follow that route, and ideally to publish also the scripts that enabled you to generate those data, those results. So I'm going to show you briefly how we do that. So in addition to the single subject, we also you also have access to the multi-subject. So you should have that as well. It was part of the example data. multi-subject is just 3 different subjects called 135, sorry. And importantly, the file, there is a convention for the file names, and we follow the BIDS convention. BIDS stands for brain imaging data structure. And thanks to this convention, your batch script will basically know that you have to loop within the data folder, and inside this data folder, it will find all the subjects and then process all the subjects using the same convention. So going to run it and then explain you briefly how it works. So we go to the multi-subject data. I have the parameters file. So first I want to do a chmod 775 star to enable to execute my bash script. And then I run SCT run batch, which if I run the help, it tells you that basically it needs a parameter file and a script file. So my parameter is parameters.sh and my script file is process data. So I'm pressing enter and that's it. So I have 8 cores in my laptop, and so it can basically use 1 core per subject. So it does a parallel processing as well. So now the question is, what is inside parameters and what is inside process data? So we can open the parameters. And you can see that it's basically, so you don't need to understand that, that line, but it basically says that path parent is a variable, and it's looking for the path where the parameters.sh file is located. That's just a shell command to get that variable. And then these are just a bunch of definitions that are used by the script. It says that the data are located under the folder data. The results will be put under a folder called results. The QC report will be put there. The log files will be put there. And very importantly, we talked about some algorithms failing, and sometimes you have to do manual adjustment. How do you deal with manual adjustment in a fully automated pipeline? The way we suggest to do it is you run your pipeline the first time. You look at the QC. You identify the subjects that require modification of the segmentation. You correct the segmentation, and then you save it somewhere where the hard drive will not crash, or you back it up, or you make sure that you keep those manually corrected segmentations. And then you rerun the same command, and the batch file, I'm going to open the batch file now, which is process data, has a couple of functions that are called label if does not exist, or segment if does not exist. And it will look in the seg manual folder if the segmentation exists, if it was manually corrected. If it does exist, it will use it. If it does not exist, it will segment it. Right? So let's say if your segmentation fails in 5% of the case, in like 1,000 subjects, then you just have to manually correct a couple of subjects. You save the segmentation somewhere, and then you can rerun the entire script fully automatically after you've done the manual fixes. Okay. And then the other variables are just technical details about the number of jobs. If you're running into a cluster that has 128 cores, then you can just replace that value with 128. Okay. So it's still running. And while this is running, we can basically move to the rest. So the rest of the course material shows the kind of outputs that you get, right? You get a CSV file that has the different subjects with the value of the cross-sectional area, as well as the MTR inside the dorsal columns for each of the subjects, right? So each row corresponds to a particular subject. This is the QC report that is actually being generated as I'm speaking. So we can go to the result folder, QC index, and if I click on it, I see that those things have already been processed. Vertebral labeling for all my subjects, segmentations, and so on. Right? And if I do a refresh, then more functions, more processes will be appearing here. There's also a log folder. If you have any error, if something crashes, you will have this process file will be renamed err.process. And so it tells you that someone, some processes crashed, some subject crashed. And if you open it, it's a log file of all the functions that have been run. So you can basically track down everything that's been done with the SCT version and so on. Okay. I already talked about that. If you need to manually correct the segmentation. So the last part, we are almost done. I think it's the very first time in the history that we finish the SCT course entirely. So subject-centric versus template-centric, that's a question that sometimes comes. Here we've done all the analysis inside the subject space, but you could also do that in the template space, right? There are pros and cons. We can discuss that through the forum, for example. That's technical detail. We don't need to talk about this. We've talked about this, the fact like the acquisition parameters do matter. SCT is designed, to accommodate as many parameters and contrast as possible. But obviously, if the image quality is good at the first step, at the first stage, then you will get more reliable results. So, I encourage you to look at the proposed generic protocol. This is wrong. I'm going to remove that. If you need help, you can look at the usage of every function. You can also ask questions in the forum. We are very friendly people, and we try to answer your requests in a timely manner. So you see that many people ask questions, and then when when we have the solution, we basically follow up on the thread. So please don't hesitate to ask anything you want, or to also suggest some feature that you would like to see. Finally, if you would like to be added to the mailing list for those events, feel free to subscribe to the mailing list at this address. There's been already a couple of courses. We can soon add a picture of you for this for the London 2020. And if you would like to contribute to SCT, you're more than welcome to. We have a contributing page, so feel free to check this out. And finally, I would like to thank everyone in the team contributed to this software package, as well as the collaborators, the sponsors, and of course, all of you, all the users, for the precious feedback. Thank you. Any questions? All right, so I think time for a beer.